So let's look at problem 17.1, and in the context of this problem I'm going to try to explain all of chapter 17. So this could be a long video, but hopefully it'll be instructive. Okay, so problem 17.1, we have a Ferris wheel and we want it to rotate 12 rotations per minute, 12 RPM, so that's pretty fast, right? 12 times around in a minute. So what's that? Once every 5 seconds. So it's going to spin around once every 5 seconds. So it's a little bit crazy. And we want the person riding it, we want them to be going, or at least I don't, but this person managing it, it wants it to go 200 miles an hour. Okay, so you're going to have a pretty fast wind in your face. So that will be a very exciting carnival ride. 200 miles per hour whipping around this thing every 5 seconds. And so, yes, that's what we want. And from problem 16.5, which you have to have done problem 16.5 to do this problem, which is a little bit annoying, so we're just going to do 16.5 again. But in 16.5 they said you start at this angle theta, which I'm going to call theta 0 for time 0, and it takes you 1.3 seconds to get to the top. So from that information, in 1.3 seconds, we can figure out what that starting angle is. And I guess that's the angle where you get on or something, or it turns to where this person starts, so whatever. So we're going to have to figure out this theta 0, and that was what problem 16.5 is about. And we'll redo that because it's a good review here. And then the point of chapter 17 problem, of this problem, is we want the coordinates of this person. Where is this person as a function of time as they whip around this thing at 200 miles an hour, which is 12 rotations per minute. Okay, so that's the overall idea here, and again we're going to kind of do 16.5 with the 17.1 problem. So first we got to get rid of these crazy units. 12 RPMs, 200 miles per hour, we got to get feet and seconds because everything else is in feet. The Ferris wheel's 4 feet off the ground. And we want the radius of the Ferris wheel in feet. That's one thing we got to figure out. And rotations per minute, we want radians per second, so everything's in feet and seconds, and radians is a natural unit. So that's the first thing we got to do. So let's change miles per hour. So our velocity is 200 miles per hour. We want feet per second, so we know that that's, let's see, 5,280 feet is the same as 1 mile. And we know that an hour, put the hour in the top, is the same as 3,600 seconds, 60 times 60. Make sure we did it right. The miles cancel, the hours cancel. We're left with feet per second. Plug that into your calculator and you get 293.33 forever. We'll just keep it like that. That's the speed they want to be going, 293.33 feet per second. Now we need omega. So the angular speed is, they give us 12 rotations per minute. We want radians per second. So we multiply by 2 pi radians, 1 full circle is 1 rotation. So the rotations cancel. And we want seconds, so put the minute at the top. 1 minute divided by 60 seconds. Minutes cancel. Let's keep it perfect. We have 12 times 2 pi on the top, so that's 24 pi on the top divided by 60 on the bottom. We're going to have radians per second. So 24 divided by 60, both those can be divided by 12. So that would be 2 on the top. 24 divided by 12 is 2, so 2 pi, and on the bottom 60 divided by 12 is 5. So 2 pi over 5 radians per second. And we could make a decimal out of that, but let's just leave it as 2 pi over 5 to keep it perfect, even though this one here isn't perfect. But okay, that's our omega. Now we know that the velocity is omega r. Remember our 3 formulas you got to remember from the last chapter. Velocity is omega r, arc length is r times theta, and theta is always in radians, And the other one is that the angle you turn it, theta, is the angular speed times the time. That's just like distance is velocity times time. Angular distance is angular velocity times time. Those are our three formulas. We're going to use this one right here. We want the radius of our Ferris wheel. So the radius is v over omega. Our v is 293.33 feet per second divided by our omega is 2 pi over 5 radians per second. The seconds VR, yep. So all we're left with is feet. Radians kind of disappears as a unit. It's a natural unit. You don't really need to write it. That's why we use it, because everything just works out. So when you do that, the radius is something like 233.427 feet, keeping a lot of decimal places. So that is how big the radius of our Ferris wheel is, which, you know, that's not quite 100 yards. It's a very, very big Ferris wheel whipping around really fast. Okay, so that's our radius. Now we can figure out theta 0, the starting angle. They say it takes us, it takes 1.3 seconds to get to the top. So theta 0, that angle is omega t. So omega is, it's turning at 2 pi over 5 radians per second. 2 pi over 5 radians per second times t in seconds is 1.3 seconds. And it's radians per second, so this is going to be in radians. And when you do that, you get, it's about something like 1 point, let me just do it out. So 2 pi over 5, 2 times pi divided by 5 times 1.3, 1.633, 1.633628. And actually that's not theta 0, that's all the way to the top. Okay, so really, yeah, so theta 0 is basically, okay, I shouldn't say this, I should erase that. Theta, the angle it goes in 1.3 seconds is this, 1.633628 radians. That's the angle it turns. But we want to know how far below 90 degrees that is, because that's how long it takes to the very top. So 90 degrees, so we want to take off, can't see that there, so you want to, it takes 1.3 seconds to get to the very top. So we want to know how far that angle is below 90. So what we got to do is take away 90 from it. So actually theta 0 is 1.633628 radians minus pi over 2 radians, because 90 degrees is pi over 2. And that's how far below the 90 is, right? It takes 1.3 seconds. The angle to get all the way to the top is theta. And we want to take away 90 to get that little angle. How far below that started? Okay. And when you do that, you get 0.06283 radians. That's the starting angle. The starting angle is that far below 90. Really, we always call in math this is 0, just so you got to have a starting point. So everybody agrees that a horizontal line starting at 0 and counterclockwise is a positive direction. Right, that's what you always do. Here's 0, 30 degrees, 60 degrees, 90 degrees, whatever. So this is actually negative. So really, the starting angle, that angle there is equal to 0.06283, but if we want to actually measure it right, we should say actually it's negative that, right? Because that's how far below it is. So just keep that in mind. That's kind of like a negative angle. Okay, so that is section problem 16.5. Now we have all that information, so we can actually do 17.1. Okay, like I said, this is going to be a long video. Okay, so now 17.1 says impose a coordinate system and find the coordinates of Tiff at t seconds after she starts the ride. Okay, so this person Tiff is on this thing starting at this angle theta 0 right there, and we want to know where she is as she goes around the circle as a function of time. We want a formula that tells us exactly where she is as she goes whipping around this circle. Okay, so this is what chapter 17 is about. So here are the formulas. Here is the way this works. Her x position, where she is in the x direction, is, since she's going in a circle, it's the center of the circle. The x coordinate x0 is the center of the circle. That's what we'll call that there. Plus r cosine omega t plus theta 0, which that's her starting angle. We already know that, right? And here theta 0 is negative, okay, because we always consider this as 0. So if he starts below that, we have theta 0. So that's what it is. And her y position is the center of the circle, and the y coordinate is in the circle, plus the radius of the circle, and it's the sine of omega t plus theta 0. Okay, so why does this make sense? Again, so first off, on a circle, and this is what you need to know forever, or at least this class is over, on a circle, if it's centered at the center at 0, 0, and let's say the radius is 1, so it's a unit circle, right? So we have a unit circle, which means the radius is 1, which makes the math easy because then the radius is 1 and we can ignore it. Then the coordinate of its x-coordinate, the x-coordinate, people decided to call the x-coordinate given by a function, that's the cosine of the angle. So if you go some angle theta around, the x-coordinate is given by the cosine of the angle, and the y-coordinate is given by the sine of the angle. That's kind of the definition of sine and cosine. So when theta is 0, when you're just starting right there, the x-coordinate is 1, right? So we need a function cosine that's 1 here, and then as theta goes to 90 degrees, or pi over 2, then there is no x-coordinate, right? It's 0. So the x-coordinate is 0 there, so cosine of pi over 2 is 0. As we go around to here, to a cosine of pi, or 180 degrees now, we get negative 1. So so cosine of pi is negative 1. Go around to here at 0 again at 270 degrees, and then back to 1, and it keeps going in a circle. So the function cosine tells us the x value as we go around a circle of radius 1. And the sine theta is a function that tells us what the y value is as we go around this circle. So here the y value is 0, so sine of 0 is 0. At 90 degrees, or pi over 2, the y value is 1, right? We're all the way at the top here. So sine of 90 degrees is 1, and then we go back to 0, go to negative 1. Sine of, what's this? So sine of pi over 2 is 1, sine of pi is negative 1, sine of pi plus pi over 2, which is 3 pi over 2, or 270 degrees, is negative 1 again, and then back to 1. So that's one way to define sine and cosine, just saying what the x and y coordinates are as you go in a circle. So we also know that from our formula up above that theta, the angle you go, is omega t. So here, instead of writing theta, we just put omega t, because that's what it is. And if the radius isn't 1, if the radius is some other number, then the x and y coordinates are just r times the cosine value. So if the radius is 2, you just multiply everything by 2. So that's where the r comes in. So that kind of makes sense. You just multiply 1, cosine and sine, biggest they can be is 1 or negative 1, and then multiply them by the radius to make that bigger. And then if we shift the starting point of the circle, the center of the circle, we just have to shift the coordinates there. Okay, so again, why does this make sense? So we're taking the angle where you are at any time is the starting angle plus how far you've traveled given in the time, right? Which is omega t, how far you've traveled from the starting angle. So that's why this formula makes sense, because this angle inside is theta, and again, theta is where you start plus how far you've traveled. So hopefully that makes sense. These formulas then make sense. So in this case, x0 is 0, because let's put our center of the circle right there. Y, because here we'll say that here's we'll have this being 0, 0 right here. That point there is our origin down here, which kind of makes sense. And so the x center of the circle is 0, but the y is the radius plus 4. And we already figured out the radius was 233.427. So the y value here is 237.427. Okay, but this one's 0. So now we can say what these things are. Oh, and theta 0 is negative this, right? And we know what omega is. We figured it out from up here is 2 pi over 5. So now we just write everything in. So x is equal to, x0 is 0, so you don't have to write it. The radius we figured out was 233.427. So x is equal to 233.427. Oh, and this is part A here. That's the radius times the cosine of omega. We figured out omega was 2 pi over 5. So 2 pi over 5t minus, because the starting angle is minus, 0.06283. And we don't have to write radians. We just, if it's not anything else, we know it's radians. That's the x. Now the y is the y starting point, y0, which we already said was the radius plus 4, which is 237. So 237.427 plus the radius 233.427 times the sine of all the same thing. 2 pi over 5t minus 0.06283, keeping lots of decimal places, which is what they do in their answers if you look them up in the back of the book in the PDF file. So we want to match them. Okay, that is the x and y coordinates. So that is one major factor of chapter 17 that I want to go over here. That the cosine and sine are basically where the x and y coordinates as you travel around in a circle. That's a perfectly good way to define cosine and sine as far as circles go. And so then you get these formulas, and then it's real easy, just kind of plug it in and being really careful with omega and radians and all that kind of stuff, which we were up here. All right, that's part A. Let's see what part B is. Part B says, Tiff becomes a human missile after 6 seconds, which makes sense. She's going 200 miles an hour. So after 6 seconds, she flies off the ride. Find Tiff's coordinates the instant she becomes a human missile. Oh, so all we got to do is use our formulas for part A here. So let's, I should just do it on the same piece of paper. I think I can fit it in. So B, t equals 6 seconds. So all you do is you plug in 6 seconds here. Which, okay, is going to be a lot of work. So x is going to be 233.427 cosine of 2 pi over 5 times 6 minus 0.06283, which is equal to, so now it's a calculator problem. Make sure, by the way, your calculator is in radian mode. That's super important. Or else, right, this isn't going to work. So you have to make sure when you take the cosine of this, calculator in radian mode. Then the y value is just this other one, 237.427 plus 233.427 times the sine, oops, not parentheses yet, times the sine of 2 pi over 5 times 6 minus 0.06283, keeping everything in radian modes. And then we just get an answer. And if you do that really carefully, you should get that it's 85.93. So her x coordinate 85.93 feet above the ground, and her y, that's how far she is to the right of where she started, right? 85.93 feet. And then how high she is off the ground would be the y coordinate, which is 454.45. 454.45. Okay, so that is her x and y coordinates. You just have to plug those things in and being really careful with radian mode. So if you're using a calculator like this, the way you change from radians to normal, see right now it says degrees right there. We want to be in radians. You just hit this DRG button, and you can choose, and you hit the arrow and you say you want the underline to be under radians, and then you hit enter down here, and it saves it for you. So now it'll say radians on the bottom. And if you want to go back to degrees, you do the same thing. You hit that button and you just move the arrows where you want to be. So really, really be careful of that. Sometimes you might want to use degrees, but most of the time you want radians. So be really careful that you have that radian button there. If you're using one of these, if you're using another calculator, you'll just have to figure it out. But that's one place where people make a lot of mistakes, is not having it calculated in radians. Okay, that's part B. Now part C says, find the equation of the tangential line along which TIF travels the instant she becomes a human missile. Sketch a picture indicating this line and her initial direction of motion along it when the seat detaches. Okay, now we figured out that, they want to know after 6 seconds, okay, after 6 seconds. Well, let's see, we already figured out that it takes her, she goes around at, how many RPMs? It was 12 RPMs, so every 5 seconds she goes around the circle, right? 12 times a minute, which is once every 5 seconds. So she starts here, so 5 seconds she's back here again, and 6 seconds she's gone, it's 1.3 to the top, so she's somewhere up here. Okay, she's going to be somewhere up here because 5 seconds to go around, it takes her 1.3 to get to the top. That's what we figured this out. So she's going to be somewhere right here when she flies off. And so when she flies off, she's going to be going like this, right? Somewhere up like that. Because when you fly off a circle, you keep going in the direction the circle goes. And then, of course, gravity is going to pull you down and you'll fall. But we're not going to worry about that. Right when she flies off, she's going to be right here going off in that direction. Okay, so what they want to know is they find the equation of the tangential line along which TIF travels the instant she becomes a human missile. So we want the equation of the line right there. So for a line, we need a slope and a point. So first we got to figure out that point, and then if we know the point, we can figure out the slope because we know the x and the y values, and we can figure out the point. So first we got to figure out that point, and that's when t equals 6 seconds. And the nice thing is we already did that, right? That was part B. We have the point. So part C here, we say our point, part C, our point was 85.93, and we know we're dealing with feet, so I'll just leave that out, and then 454.45. 45, that's our point on the circle, which we know is somewhere right up here. And let's see, can we figure out the slope? Here's our circle. The slope is going to be the y value divided by the x value, right? Slope is always y divided by x. So the y value, and this, however, that's above this point right here. So we need to figure out how high above this point it is and our x value over. Well, the x value over is the x value. That's 85.93. So that's 85.93. The y value, we know it's 454.45. That's off the ground. That's all the way from the ground. It's 454. We want to know what it is from this middle point of the circle. So let's see. We got, this is 4, and then we have a radius. So we got to subtract the radius of the circle plus 4 from 454.45. So the y value is the radius of the circle, which we figured out earlier was 233.427 feet. So it's 454, her position, minus the radius plus 4. So 233.427 plus 4 feet. And we do that to get our y value. Again, the x value is right because we started off at 0 here, so that's all good. So I get 454.45 minus 237.427, which is 217.023. That is her y value as she falls off. That's the value above the center here, right? Okay, so now the slope then is just the y over x, which is 217.023 divided by 85.93. right? Rise over run. So that looks right. And let's see, it's a positive slope. This is a positive slope. So makes sense it's going to be positive. I get an answer here. So divided by 85.93. And I get 2.52558. That's how many decimal places should I keep? 2.52558, let's say. That's the slope. Now, that's the slope of this line. We want the slope of the tangent line, which is going to be perpendicular. So the slope of the tangent line, so I'll put that little t here, is negative 1 over that, right? Negative 1 over 2.52558, which is why it's a good idea to always keep numbers in your calculator. So 1 over that, and I get that that's equal to negative 0.395949, let's say. It's a lot of decimal places. Okay, that's the slope of the tangent line. Now we have a slope and a point. We can figure out the equation for the line. So finally, we can say y minus y1 equals mx minus x1. My voice is still working. Y minus, okay, there's a lot of decimal places here, but oh well. So y1 is, yep, here's our point. So y minus y1 is 454.45 equals the slope, negative 0.395949 times x minus 85.93, and a lot of calculating now and not making mistakes. Let's see. So y then is equal to negative 0.39, and again, how many decimal places should I keep here? 0.395949x. See, this is negative times negative, so what's that? So that's times 85.93. That's plus 34.024, let's say. Adding this to that side, so plus 454.45 plus 454.45. We finally get that the equation of the line is negative, and I'm going to round off to 3 here, so negative 0.396x plus, I'll round off to 3 to 48.474. 48.474. And that is the equation of that line. It makes sense, it's a negative slope. It's right, negative slope. It's going to be going like this. It goes through that point, which we knew, so it's up there, and it's tangent to the circle. Okay, that's problem 17. A whole lot to it. You got to remember chapter 16 really well, and get comfortable with sines and cosines. So these are the main new formulas we'll be using a lot. That the x position is the center of the circle, plus the radius times cosine of the angle that you're at, which is the starting angle, plus how far you've traveled, omega t. And the y is the same thing, but it's sine. Exact same thing, but sine. And again, sine by definition tells you the y position on a circle, the height of a circle. So y position is always how high above or below you are the axis, and the x position, cosine, tells you how far this way you are. So cosine is horizontal, and sine is sideways when you're dealing with the unit circle. And that's the major thing to remember here. Okay, good. Hopefully that makes sense. And you've followed all the way through this almost half an hour video. Good job if you listened all the way. You get extra points.